All right. Well, let me start by expressing my regrets for not being there in person. I really wanted to be part of the celebration, and well, I'm currently myself celebrating my 10th day after my positive COVID test, so it seemed to be the smart thing to stay home. So I'll do my best to keep the celebration going by starting with mentioning George's 1959 paper, actually one of two. I noticed this is the one that I always think of, but George also had a very nice paper about the colors of aurora Lyrae stars in that same year. And I think that must have led on to the Sturch's work and the Sturch law that Barry talked about. So it was a good year for aurora Lyrae stars, I think. This is one of the spectra from his 1959 paper showing the calcium K line and the hydrogen lines. I'm sorry, it's kind of a crummy reproduction, but right, he used the spectral type of the hydrogen lines and the difference with respect to the calcium line to come up with this delta S, this difference in spectral types that we know well is associated with metallicities today. So I'll talk a little bit about my work on this and how it has moved forward and not over the years. Maybe talk about a little bit about some of the joys and sorrows of working with aurora Lyrae stars that I suspect many of the people in the audience can relate to. And I want to mention that this is work that most recently has been done with my master's student, Irina Plox, who graduated last summer about this time. And so I owe a great deal of thanks to her for moving this project forward. So we know that aurora Lyraes are great tracers of old stellar populations. Giuseppe's done a better job than I can do of describing some of the benefits of the non-kinematic selection that they provide. And I think we've also heard from Giuseppe and Heather and others that the solar neighborhood is particularly well studied now with hundreds of spectroscopic metal abundances, and as Gaia has been kicking in with its astrometry, really good motions as well. And so some years ago, he says, being non-specific, I was working to try to extend some of this work into other galactic regions to study in situ different parts of the galactic halo, including a region in the inner halo, which I'll talk about today, a region above and below the galactic plane, roughly at the solar circle, and some work with Heather and Paul on bulge aurora Lyraes. And in all of these cases, we obtained photometry and spectra of the aurora Lyraes that we were working on. And sadly, in all of these cases, some of those sorrows that I mentioned, some of the complications involved with working on aurora Lyrae stars led me to some concerns about the data that let me put the projects down for a while, and I didn't pick them up again until recently. They remained dormant for quite a while. But some of the new data that's coming along online and some of the methods that have improved over the years have caused me to pick this up again. And Irina in particular, and her enthusiasm for aurora Lyraes and ideas of accreted halos and interactions with satellite galaxies really drove this forward over the last couple of years. So I'll try to move forward and give you some preliminary results of this inner halo study reboot as we go forward. Let me start by telling you a little bit about what the project looked like initially. We picked out about 100 aurora Lyrae stars in the inner halo of the galaxy from photographic surveys. Basically, we went into the general catalog of variable stars and picked stars in certain regions of the galaxy above and below the plane on either side of the center of the galaxy in these 4 regions. And we used the photographic magnitudes available at the time to choose stars that were along lines of sight that would put them roughly at their tangent points of their galactic orbits. If this is the sun up here and this is the galactic center, a given star, by measuring its radial velocity, we would in large part measure its rotation about the galactic center. In order to refine the distances and understand their positions in the galaxy better, we did some photometry using the 0.9 meter telescope at Cerro Tololo. And this is an example of one of the stars where we've got 1, 2, 3, 4, 5, 6, 7 data points, rather sparse photometry in terms of time series. But we used the existing period that was available in the general catalog of variable stars to give us a very good first estimate of what the period would be, so that we could fold the light curve and fit a template, or actually a series of templates of RRAB type light curve shapes, one of which is shown here fitted to the data. And you can see it seemed to do a pretty good job. So that gave us some confidence that we could measure the mean magnitude of the star on sort of current Johnson V photometric system. And we could also determine the time of maximum. Knowing the period, that would also allow us to predict a time at which we should take the spectrum to give it a best shot at being a very high quality spectrum in terms of avoiding the rising branch. And George has talked about the emission lines and the complications that might put into radial velocity measurements. And at least at the time, we were also thinking that observing near minimum light would be an advantage to us, just in terms of a better quality delta S type measurement. So we got that photographic work done and actually published. We also took a large number of spectra for 84 of the stars. And again, with H delta and H gamma here, we were able to sort of represent the star's temperature. And with the calcium K line here, which is also, is dependent on temperature and calcium abundance, we were able to work out the calcium or metal abundance of the star. And we felt like at the end of this process, we understood the metallicities of the stars pretty well. We also used Doppler shifts to measure the radial velocity of the star. And that's where we started picking up concern, I guess. Here's results from that preliminary work in terms of the metal-rich stars in the sample and the metal-poor stars, again, breaking like Heather did at a FE on H of about -1. We only had a handful of stars because we were in situ out of the disk, out of the plane, but we did have a few, I think 5 stars that gave the steep rotation in this plot, this Franken-White style analysis plot, and small velocity dispersion that's characteristic of the thick disk. Among the more metal-poor stars in the sample, we had a slight prograde rotation, but a rather large velocity dispersion. This set of velocities had a rotation velocity of about 24 kilometers a second, but this large velocity dispersion along the line of sight of almost 150. And that's where my worries really set in, because that's quite a lot larger than I was expecting. It's very much larger than in the solar neighborhood. And it's also larger than a set of inner halo globular clusters that Bob Zinn had studied at the time. And so it led me to worry that there were problems with my radial velocities in all the steps, both in timing the spectrum and perhaps in correcting the radial velocity to the center of mass velocity of the star. So at all these steps, I just had these nagging concerns. And as I said, it caused me to put down the project while I sort of picked up some other projects to work on, and it just lay dormant. I suspect most of us in the audience can point to something in their career that they put down and picked up later, hopefully. The picking up, the updating, involves improving the photometry. I hope improving the radial velocity measurements, And as I'll show you towards the end of the talk, I hope some improved ways of subdividing the sample and bringing in the Gaia proper motions that Heather was just talking about. So improving the photometry turned out to be a little more complicated than we thought. Irina went into the Assassin database of variable stars and pulled out both the periods for the stars and also the light curves for the stars. And here's one of the stars in our sample. You can see there's a bit of scatter to the light curve at this magnitude of about 14.5 or so. But a lot of data points so that we believe that the period is very well determined. And we also actually downloaded the data and ran our own period analysis using Fourier methods. And so we could compare our results with the Assassin results, look for aliasing and things like that. And so, you know, that's making the light curves to me is always one of the joys of astronomy. When you pop up a light curve and it works, there's nothing quite so good as that feeling. When it doesn't work, when you see that nasty Blasco effect showing up or period aliasing messing up your light curve, those are the sorrow moments. We moved forward as best we could. I'll show you some of the results that Irina had from that. But ultimately, our plan after inspecting the quality of the Assassin photometry was to fuse the Assassin periods with the old CCD photometry that we had obtained. The sort of hybrid of those two methods we thought would give us the best results in terms of measuring the mean magnitude of the star for distance estimates, and also determining the time of maximum so that we could predict the phases of our spectra as well as possible. I'll cover these other things as we move forward through the talk. So in terms of the photometry, Irina compared the period that we had initially from the general catalog of variable stars with the period that was available from the Assassin data and our reanalysis of the Assassin data. And you can see that most of the periods behaved reasonably well. We weren't too far off with our GCVS periods. There were a handful plus of stars that needed major period revisions. We made minor adjustments to the periods, to the initial GCVS periods of about 60 or 70 of our sample, and about 35 or so of the stars were so nearly identical to the GCVS period that we didn't really need to adjust them at all. But perhaps most importantly, we were able to use the Assassin data to assess the uncertainty in the periods. And using the uncertainty in the periods and the time of our photometry, we were able to put both a solid prediction on the time of our spectra and also an uncertainty on the phase of our spectrum. And that led us to have a lot more confidence, as I'll show you, in our radial velocities. So that was an important major step for us, settling the periods and feeling confident about the periods. Here's a couple examples of how we fused the photometry together. Here's the original light curve and fitted template from the 0.9 meter telescope CCD photometry and the original GCVS period. And for this star, 508 Acole, it was one of those joy moments, right? A beautiful light curve, a beautiful template fit. And so we were feeling pretty good about this star even initially. The Assassin data for this star is quite good. It's one of the brighter stars in our sample, so the signal to noise is good here. And when we fused the Assassin period with the 0.9 meter data, we got a really terrific, joyful sort of light curve. This star, not so good, 872 Ophiuchi. Initially, we had enough scatter that we were concerned about the period. This is one of those red flag stars that really got me worrying about how good are our periods. The Assassin data's got a fair bit of scatter too, because the star is quite a lot fainter, and perhaps there's some Blasco effect involved in here. But we felt like there were enough data points so that we could pin down the period pretty well. And when we did do that and improve the period and fold our initial data with it, we still had some scatter. So this led us to think that this might be a case where the stars got Blaschko effect, and we would really need more data points in the light curve to pin that down. But by and large, we felt like we had improved the photometry and the timing of the photometry quite a lot as we move forward. Aliases are still a problem even with the assassin data. With those new timings and phases of our spectra in hand, we were able to go ahead and update our radial velocity. One of the things that we found along the way is that cross-correlating with synthetic spectra seemed to produce better results than cross-correlating with the original radial velocity standards that we had observed as part of our observing. And so we think that helped a little. We also had access to improved radial velocity templates. We've been using a series of templates from CESAR from about 10 years ago, which are interesting because they scale the radial velocity amplitude of the template with the with the photometric amplitude of the star to better approximate the sort of pulsation behavior of the Aurora Lyrae star. And so here's another good example where we've got our two back-to-back spectra with high signal to noise and relatively small radial velocity errors, and really good timing so that you can barely see the uncertainty values in the phase, and the fitted template and its mean or systemic velocity are well defined for this star. Here's one of the poorer cases where we've got lower quality signal to noise spectra, so larger error bars in our back-to-back spectra, and also much larger error bars in our phase, so in the timing component of our analysis. But we still feel like we've got a fairly good fit to the of the template to those data, and a fairly respectable and reliable mean or systemic velocity for the star. And so we moved through that process with all 80 plus Aurora Lyrae stars. And as a final check, we decided that we could look at the Balmer line equivalent widths, so essentially a temperature indicator, as a function of our predicted photometric phase at the time our spectrum was taken, with respect to data that we'd gotten with a project with Bob Zinn a couple of years ago. The X's again represent sort of the expected position of stars. The dots here represent our high signal to noise spectra, and they agree very well with the expected positions. The blue dots are lower signal to noise, and the red dots are in progress work. And you can see they have a little bit more scatter, but by and large, our photometric phases seem to hold up in terms of the context of the actual temperature profile of the stars. So we
Andy,
have
3 minutes, please.
Very good, thanks. So we have very good confidence that our radial velocities are much improved. If I plot the metal abundances of our stars against the height above the galactic plane, we see the more metal stars, more metal-rich stars, as Heather showed, are diskish, and the more metal-poor stars are haloish. If we plot metallicity against the radial velocity, we see again diskish behavior. The most metal-poor stars seem to have a larger velocity dispersion, and the intermediate halo stars have a somewhat smaller velocity dispersion. And so when we go to the Franken-White analysis, for the inner halo sample, our disk stars still have that fast rotation and moderate velocity dispersion appropriate to a rotationally supported kinematic population associated with a thick disk. The metal poor grouping below minus 1.8 in FE to H have a large velocity dispersion, almost 170 or so kilometers per second, and perhaps a retrograde motion, though the errors are large there, that might indicate that some or all of this population is from an accreted set of dwarf galaxies. And the more metal-rich halo component seems to have a positive, slightly positive prograde rotation and a smaller velocity dispersion that might indicate an in situ sort of collapse and spin-up type formation, or perhaps a thin disk that was puffed up by interactions of moderate size infalling galaxies. So last thoughts here. Going back to the plot that Heather showed and was originally in George's 1959 paper, the period versus metal abundance plot, we still see that general trend. I'm curious to split off the stars that have longer periods at a given metal abundance and may be associated with stars that have evolved from the blue horizontal branch versus stars that might be more involved in sort of zero age horizontal branch stage evolution that might be like the Osterhoff 1 population. So that's next on my list of things to do. And we've got some hint that there might be some stellar streams in our data, but that needs to go forward. And finally, like Heather mentioned just recently, the new data releases from Gaia are giving very high quality proper motions that yield very high precision velocities, tangential velocities, even at this large distance of 6, 8, 10 kiloparsecs away from the sun. And so that's really going to open up this field. So again, as I finish, a shout out here to the Modern Time Series photometry that's available and in progress and coming with the Vera Rubin Observatory. That's going to make sample selection really advantageous and provide really good quality periods and timing and photometric properties for determining distances. This inner halo project, I hope, will continue to move forward, and the Gaia astrometry will just be transformational as we move into the next era. And again, I want to thank Irina Plox, who's now a PhD student at the University of Iowa, for her work and patience with me throughout this whole process. Thanks very much.
Thank you, Andy. Again, we have time for 1 or 2 quick questions.
My question is about the Lyra and stellar streams. Can you tell us a little bit more about, like, are those presumably quick galaxy streams or globular cluster streams, and how many per stream, and sensitivity?
Sorry, I couldn't hear much of that. Could I get a translation, please?
It was basically asking you for more information about the stream possibilities.
Oh, okay, yeah. Let's see. So here we've separated out the Franken-White solutions for stars above the galactic plane and below the galactic plane, using the same colors of disk, intermediate halo, and metal core halo. And this grouping of stars here, about 5 stars that are very closely together kinematically, but also very close in metal abundance and spatially, are an intriguing group that Irina picked out. And so one of my projects in the coming weeks is to see what their Gaia proper motions look like and see if they still remain solidly clumped together. There's also an interesting absence of stars here, where we see it, stars well distributed everywhere. And so it's almost like an anti-stream, a hole in perhaps in kinematic space here.
Well, thanks again, Andy, and good luck with your health. And let's thank him again.